Hi, in a previous video, we determined the wave function for a tunneling problem. The tunneling problem in particular was this rectangular barrier potential. It had a width we were calling W and a height that we were calling U sub 0. So let me put in the W so that it was of width W, right? That's a distance, some number of nanometers or something really small, right? Quantum mechanics problem. And the potential is 0 everywhere except for during the barrier or for positions associated with the barrier where the height is U sub 0. And tunneling is the situation of considering a particle whose energy is smaller than the barrier height. So classically, this particle that doesn't have enough energy to cross the barrier bounces back from the barrier, right? It's pure reflection classically. But quantum mechanically, we get a mixture of a probability to be able to transmit and one minus that probability to reflect, right? It's either going to transmit or reflect. There's no other options. All right, so what we found from using Schrödinger's equation is this regional solution for psi. So psi, we solved the time-independent Schrödinger equation, and we got the wave function shape in the three regions. But you can see there are 6 undetermined constants so far. So P, Q, R, S, A, and B. A and B are the constants associated with exponential growth and exponential decay within the barrier. So this, very carefully, I'd like you to note that this is not a wave. It's an exponential growth and an exponential decay mixture. But outside of the barrier, where the particle classically can live, right, it is a wave with a wavelength, if you care to understand this wave number k in terms of a wavelength. K is 2 pi over lambda, and that lambda is a de Broglie wavelength. It's a de Broglie wavelength. Here is what k means. K squared is twice the mass of our particle multiplied by the energy of the particle divided by h bar squared. This is the wave number in the region where the particle is somewhat free. And then, but beta is the coefficient up in the exponential. Beta is it's not associated with a wavelength, right? Okay, so because our wave function is not a wave within region 2. And then region 3, again, is really similar to region 1. But you can use boundary conditions. There's a continuity boundary condition at each boundary, and there's a continuity of the first derivative boundary condition at each boundary. And then there is normalization, but for reasons, if you think about it, you can figure out why. But this is actually not normalizable. Oops. And it's because it's essentially a free particle. So normalization is not something where we can get rid of another one of these coefficients. Instead, what people tend to do in this problem is calculate what are called transmission coefficients and reflection coefficients. And I'm realizing that I made a mistake in labeling my coefficients within my wave function solutions. I'd like you to notice very carefully that the meaning of this R and the meaning of this R, they are different. We're going to calculate something called the reflection coefficient, but it is not the value of this coefficient here, right? This was just I was just reaching for letters, and P, Q, R, and S were just convenient list of letters I didn't think would clash with something physical that we have to calculate later. But I made that mistake. But I'm going to show you that actually I'm going to switch it up a little bit. So, okay, so here is, so I'm going to make some arguments. Remember that for potentials that only depend on space, so these are not time, man, I've got really bad handwriting, not time dependent, right? This implies that we can write down a time-dependent wave function that would solve the time-dependent Schrödinger equation. It's just simply find the time-independent solutions and then multiply by e to the minus omega t, where omega is E over h bar, where E is the energy we're talking about right here, right? It's the energy that in our tunneling problem is smaller than u sub 0. So that's the meaning of omega that sits up in this exponential, and you just simply multiply by this time evolution factor, e to the minus I omega t. All right, so I'd like you to recall first this following fact, that e to the I angle, right? E to the I angle, or e to the I value, is cosine of the value plus I sine of the value. And what you can do with this, actually, sorry. I had to write this down because I can't remember these things. So I'm going to just cut it. Okay, so recall that you have this Euler equation, right, for how to understand if your exponential has an imaginary argument. This can give you things like, for example, cosine of theta is equal to e to the I theta plus e to the minus I theta divided by 2. And also it can get you sine of theta equals to e to the I theta minus, let's see. I think, nope, it's, sorry. Just e to the minus I theta divided by 2. I believe this is right. Yeah. Okay, so is this true? I think this is true. Sorry, actually, I realized I had to pause and go check, but it's actually divide by twice I. You can get this if you just use this equation, and you can get these two things. But long story short, instead of writing psi 1 and psi 3 in terms of cosine and sine, right, which was sort of natural because I could understand that in region 1 I have genuinely a wave, and in region 2 I have a wave. I mean, region 3 was another wave of the same wavelength because it has the same value of k. In region 2, I had some mixture of growth and decay, so not a wave. And the boundary conditions knit these things together. That was in the previous video, I described that. But the point is it turns out that there's a really nice thing you can do, right? Just it starts off as being a mathematically nice thing, but then it becomes a conceptually physical nice thing to do by rewriting or rethinking the wave functions in regions 1 and 3, not in terms of cosine waves and sine waves, but instead in terms of cosine waves and sine waves written this way. And so what I'm going to show you is, what if we instead wrote the region 1 wave function this way? So I was using coefficients p and q, but if I rewrite the wave equation, it's actually not going to give me the same coefficients. So I'm going to call them p prime and q prime, and it's going to go p prime e to the I kx, right, instead of cosine of kx, plus a different coefficient times e to the minus I kx, like this. Psi 2, I'm going to leave alone. It looks good the way it is. So this is a e to the, beta x plus b e to the minus beta x. So it's still exponential growth and decay mixture. And then psi 3 of x is, so I used r and s, so I'm going to use r prime e to the I kx plus s prime e to the minus I kx, right? So I just rewrote the wave functions using Euler's formula. And the reason I do this is, for example, if I look at psi 1, but I want to understand the time-dependent version, I'm just going to multiply through by e to the minus I omega t. So if I do this, right, I just take the space, pure space wave function, multiply by e to the minus I omega t. And what this looks like is I've got a p prime, and I've got e to the I kx times e to the minus I omega t, plus I got q prime e to the minus I kx times e to the minus I omega t. And if I go and I mix the arguments of the exponentials, right? So e to the exponential, e to the argument times e to a different argument is just e raised to the summation of the two arguments, right? That's a basic exponentials fact. So this looks like e to the I and then kx minus omega t. And then the q prime term looks like e to the minus I, and then it goes kx plus omega t, right? I get the plus sign here because the arguments have the same sign. I get the minus sign here because the arguments have opposite sign. And if you look at this, e to the I kx minus omega t, let's rewrite this using Euler's formula. It's cosine kx minus omega t plus I sine kx minus omega t. And these arguments right here are known as phase factors. And if you look at the relationship or the relative sign between the term that's in space and the term in time, there is a minus sign. So that means this is a traveling wave that travels in the positive x direction. And so is this. I've got a real part that travels in the positive x direction, and I have an imaginary part that also travels in the positive x direction, right? So these are traveling waves. Right? So what the region 1 wave function is a traveling wave in the positive x direction, right? So this part right here travels in the positive x direction, but this one over here is a traveling wave that travels in the negative x direction. So what p prime is describing, or actually let me redraw the potential. Right, so this is the potential. There is incoming or incident traveling waves. They head in the positive x direction, but there's also outgoing reflected waves. So the reflected waves are heading backwards. And that's what P prime and Q prime are. The incident waves have something to do with P prime, and the reflected waves have something to do with Q prime. And if you go over into this side, these are the transmitted waves, right? This will be in region 3. This was all in region 1, and region 2 we won't have any reason to discuss in this piece of lecture. But this transmitted wave is positive x directed, and we actually expect none of this. We don't want any of the left directed wave. What this means is in region 3, let's go force that to be the case. So here's the region 3 wave function. I don't want any left moving waves, right? Because there is no reason for them to be out there. Physically, what we're imagining is we send in from a source on the left side waves of particles, right? A ray of, say, electrons. Some of those electrons are going to reflect off the boundary, and some of them are going to transmit. But if the electrons make it to the transmitted side, there is no reason for them to come back because there is no other barrier. So we as physicists who are modeling this situation, you'll just model it so that we choose this term to be 0, which is the same as saying, right, there is a boundary condition such that I don't think that there's any physical reason to have waves moving leftward in region 3. But the reflected and the incident, right, which is associated with P prime and Q prime, and then the transmitted, which is associated with R prime, unfortunate choice of letter, you can see, looks like this. Okay, so now we're down to a transmitted coefficient, and transmitted coefficient, if I square this thing, that's like the probability of transmission. But the thing is R prime is not normalizable. So what we say instead is, instead of describing the probability of transmission of any particular electron, what we do is we back off and we say, because this is not normalizable, what we want to do instead is compare sort of the size of R prime with the size of P prime. And so instead of just calculating R prime squared by itself, we're going to calculate something called R prime over P prime squared. So this is represents how much incident particles there are coming into the boundary. This represents, right, the transmitted probability. And if you take the fraction, what this is if you take this fraction, this is what we're going to call the transmission fraction, or the transmission percent. And you'll see that actually it's a function of the energy of the particles that are incident, but also an interesting thing to keep track of is also how this transmission coefficient is related to the width of the barrier. And we're going to see that this is extremely sensitive to changes in W, right? By the way, there is also a reflection coefficient, which is also related to the incident energy and also the width of the barrier, but it is simply 1 minus the transmission coefficient or the transmission fraction. Okay, so here is what I want to concentrate on next. This is called the transmission coefficient.